Hello students, it's Dr. Sansom here. I wanted to make a quick video to talk about average atomic mass. This calculation can be a little bit tricky, but I think you'll see that it is ultimately very similar to other types of calculations you've done if you've ever calculated any sort of weighted average. So the first thing I want to do is define what is the average atomic mass. This is going to be a weighted average. We'll explain what that is in a minute. Of the masses of all isotopes of an element, and they're weighted according to their natural abundance. So first let's take a simplified example. Let's say we have an element X, which isn't a real element, but let's say there's X71 and X72, and let's say it's divided totally equally 50% of each in the natural abundance. If that's true, then when we take our weighted average of these, we're just going to add 71 and 72 and divide by 2, and we're going to get 71.5 for our average. We just do it like a regular average because there's equal amounts of them. Okay, now I'm going to show you how to do this written out the way we would do it if we're doing the weighted average and they weren't 50%. So I've got 71, that's my first isotope. I'm going to multiply by 0.5. That's my 50%. Then I'm going to add 72 multiplied by 0.5. And then when I do that, I'm going to end up with 71.5 as my weighted average. So we get the same thing regardless of which way we did it because our 0.5, the 50%, is just the same as our 1/2 that we put up here. Now, what if instead of this being 50% and 50%, we have 30% and 70%? We're going to do the math the same way, except instead of 50%, I'm going to plug in 30% and 70%. So 71 times 0.3 gives me 21.3. And 72 times 0.7 gives me 50.4. When I'm done, I get 71.7. So I want to talk about this for a second. We should notice we had more of this isotope that had a mass of 72 than we did of the mass 71 isotope. And therefore, when we take the average and it's weighted by how much we have, we expect our answer to be closer to 72 than 71, and that's exactly what we saw here. Okay, now this is a very similar kind of math if you imagine, for example, you're calculating your grade in a class, and 30% of your grade is for homework, and you have 100%. 70% of your grade is for exams, and you have, let's give you an 85% on your exam score, okay? And now you want to know what's my grade in the class. So you take your score, 100%, and you multiply by 0.3 for your homework, and you take your score for your exams, 85%, and you multiply by 0.7 for your exams. So we get 30 plus 85 times 0.7 is 59.5. We end up with 89.5 for our overall grade in the class. And of course, if this is Chem 105, we round that up to 90. So you get an A-. Well done. So this is what we're dealing with a weighted average. It works just the same way that you would calculate your grade if you were calculating an average for a course grade where you had exams and homework that were weighted differently. So let's do a real example now. Let's take the example of copper. Copper has two naturally occurring isotopes. There's copper 63 and copper 65. Copper 63 is more common. It makes up 69.17% of the copper that we find on the Earth, while 30.83% is going to be copper 65. And the mass of these, if we're going to be real precise, it's not exactly 63, it's 62.930. And this one is 64.928. So this is our mass, this is our percent abundance, and this is the isotope we're talking about. So what we're going to do here is figure out what is the average atomic mass for copper. Again, I'm going to do the same thing that I did before. I'm going to take my mass, 62.930. I'm going to multiply by the percent, 0.6917. And then I'm going to take my other mass, 64.928, and I'm going to multiply by its percent abundance, 0.3083. And when I do this, I'll do them one at a time. 62.930 times 0.6917 gives me 43.5287. I'll keep 4 decimal places for now. And then we have 64.928 times 0.3083. That gives me 20.0173. When I add these together, I end up with 63.5460. I should only have 4 sig figs in my answer because of these guys. So I'll round this to 63.55. And indeed, 63.55 is probably what you're going to see if you look on the periodic table for copper, as the average atomic mass that takes into account the abundance of the different isotopes of that element. Okay, I want to do one more example, and this is another type of problem that you might encounter, where we're going to know the mass of the isotope, but we're not going to know its abundance. So I'm going to have oxygen 16, oxygen 17, and oxygen 18, 3 isotopes of oxygen. The mass of each of these isotopes is 15.995, 16.995, and 17.999. And I know that the natural abundance of oxygen 16 is 99.759%. And I know for oxygen 17, it's 0.037%. But I don't know what the natural abundance is of oxygen 18. I do know when I look on the periodic table that the average atomic mass is 15.999. So what I want to do is calculate the percent abundance of my oxygen 18. I'm going to set up my calculation just exactly the same way as I did before. I'm just going to have to do the calculation a little bit differently. So I'm starting with my mass, 15.995, and that's my 99.759%. I'll add my oxygen 17, 16.995, times 0.00037. That's changing that percent to just a regular decimal. And then the last one, I've got 17.999, but I don't know what the percent abundance is. When I add those all together, I should get 15.999. So what I'm going to do is calculate these first two, 15.995 times 0.99759 gives me 15.956. 16.995 times 0.00037 gives me 0.00629. And then I'm going to have this number here that I can't get rid of, 17.999x, and all of that's going to equal 15.999. I'm going to subtract these two from my 15.999, so I'll get 17.999x equals 15.999 minus 15.956 minus 0.00629. And that gives me 0.03671. I'm going to divide both sides by 17.999. And I get x equals 0.00204, which would be the same as 0.204% abundance. So that's the other kind of problem that you can see here, where you know the abundance of some and not others, and you have to solve for the percent abundance. I hope that's helpful. Have a wonderful day.